Okay, we'll see if any more arrive. Welcome to this lecture number 6, I think it is, in the course Programming Distributed Systems. And what we'll talk about today is time, both actual normal time when we look at our watches and see that it is 13:16, or later we will get into something called logical time. And I think I'm going to start with one example of how problematic it can be with different clocks on different computers. So if I start by showing all these windows here, when you're using a Unix system or Unix-like system like Linux, then you can easily connect to other computers and give commands using this shell or command interpreter. So I have actually 3 different computers working here. I have first Rasputin, which is this local laptop, physical laptop. I have one computer called Jobotron, which is my computer over at my office. And I have here the one called, this one over here, called Basen, which is, if you remember the IP address you used for your UDP experiments, then it's that computer that you talk to when sending UDP messages. So we have 3 different computers, and let me start by showing some times here. If I say give the command date, maybe here on my local computer, it says 13, 18, and 14. If I give the same command over here at the other computer, the server, the UDP server, I get a completely different time, 11, 18, 26. And the reason that we have completely different times, differing with 2 hours, is that here I got the local time zone, including daylight savings time, or summertime, as we say. And up here I got UTC, which is Universal Coordinated Time, which is similar to the old Greenwich Mean Time, London time, basically. And it's just that this, if I give this flag minus U, both of them will give me UTC, and let me try to quickly press enter on both, and I got 11, 19, 21. So they seem to be fairly well synchronized when you use the same time zone. We can look at my office computer, the one called Jobotron, and let's see if that one is reasonably synchronized. If I compare my local laptop here with my office computer and try to click enter quickly, and it differs a lot here. This one is 11:19 and this one is 11:22. So my office computer seems to be a couple of minutes faster, or further into the future. If I try to compare to see what the actual time is, well, we can check with my phone here. And if I look at, well, you can check it with your own phones, or if you have a watch, if you have something that shows seconds. If I pass 45 seconds here and press U, I got 45 seconds here too. So it seems that the Basen server and my phone and this laptop are fairly well synchronized. Not my office computer though. And the reason for that is just that when I installed the operating system 1 or 2 years ago, I never set up correct synchronization of time. We have also this watch here, which I had hoped to show that it's also synchronized and show in the same time. Now it doesn't, because this is radio controlled. It receives time updates from a radio transmitter in Germany, which is connected to an atomic clock. And if I had carried this one up on the roof at home, so it could receive those radio signals, it would have shown the correct time. Now it's a few seconds off and not showing daylight savings time. But what I'm saying here is that there is a whole infrastructure of timekeeping that tries to keep all the computers, watches and phones synchronized, showing the same time. But sometimes that fails. And one thing that can cause problems is timestamps on files. And maybe you remember that we mentioned NFS, Network File System. So in a normal Unix system, you have a tree of files starting at the root, and then you can have various branches in the tree here, /usr, /home, etc. And on home you can have /home /bob. You can have /home /tom, and so on. So you have a tree of files. A bit different from on Windows, where you have these drive letters, C:, and M:. You don't have this here, you just put things in the tree. So for example, if I have an extra local disk, I can put it somewhere in the tree. It could be called USR big disk, or whatever I like, wherever I want to put it in the tree. So if I switch back to my office computer here, let's take, this one is okay. If I say DF, which means disk free, this is a way to just show the various things that have been mounted into this tree. And if you see, I have the root directory and a number of different ones. For example, big slow disk. Yeah, that's one extra disk, as I showed. I drew on the board. We have home, so there are different local partitions or different local disks. So for example, if you recognize NVMe, that's an SSD, and it has two different partitions. Here I have an encrypted external disk called flyttbar, meaning movable. So I have a number of things mounted in this tree. And the network file system allows us to mount disks from a completely different computer. So if you have a file server, you can mount disks from that one, so it looks like they're in this tree. So for example, if I go to my Boson server, I can, in the file etc exports, list which directories, which folders, if you want, I am exporting. So this one, var NFS general, is one of those. And if I change directory to that one and just, and just list all the local files. I have a make file, a C program, an older version of the same C program, and so on. And I guess most of you have seen the program make, which is standard on most Unix systems. It allows you to compile things, build projects, and it looks at timestamps on the files. So let me try this one. Here I have, let's use this one. And let's go to temporary 14th of April, that's today. I have two subdirectories here called local and remote. And local, of course, is just a normal directory on the local disk or the local SSD. And I have similar files here. I have blytest.c. And if I look at its contents, all it does, it's a C program that prints hello world version 1. And now if I use make, I can say make blytest. And if I try make blytest.c, well, it can't write programs for us, at least not in this simple way. So nothing to be done. But if I say make blytest, then it knows that, okay, I want a file called blytest. I have a file called blytest.c. So probably I want to compile that file and create this executable called blytest. So let's type blytest, and yeah. Now it used CC, the compiler, and I suddenly have this blytest file that I can run. And probably it will just type hello world version 1, right? Yeah. I can try to say make blytest again, and what will happen then? Well, it looks at the timestamps. It sees that the executable file that we just built is newer than the source code. So clearly the source code hasn't been changed since we compiled blytest. So if I say make blytest, it says, oh, blytest is up to date. You don't need to do anything. And I can do that a number of times. Or if I want to change blytest.c, correction. Oh, no Windows system. I can change this to, let's say, version 2 instead. Now, if I look at the timestamps on the files, this new version of blytest.c is edited later than the timestamp of blytest. So if I again do make blytest, okay, it will see that the source code has been changed since we compiled, so it will realize that it has to recompile blytest. Okay, and if I try to do the same thing again, make blytest, yeah, now it's up to date. And when I run blytest, it says hello world version 2, because this is the new version. This is on the local disk, no problems at all. What I'll do now is I will mount the disk from the server, the Boson server. So let me see if I can remember how to do that. No. Mount.nfs. And how do I tell the system where to find these files? Well, I use the IP address of the server. And what was it called? It was called var NFS general, so let's copy that part here. And put it somewhere in the file tree. So since we had local and remote as subdirectories here, so I'll put it in remote. So, and now if I do df to see what partitions and disks I have mounted, I will see that, okay, I still have like big slow disk and various local disks, but I also have this one, which is a directory on the remote server. And if I do ll or maybe cd remote and list the files, this you may recognize as the same files as I watched at the server. So for example, if I create a small file called new file, before I do that, it doesn't exist here. But if I do touch new file, yeah, you can see that there is a new file called new file on the server. And if I do list the files here on my local computer, the one in my office here, suddenly new file appeared here. And there is some problems here with the ownership of the files. You see that new file is suddenly owned by Wizard, while up here at the remote file server, it's owned by a user called Debian. But we have access to these files, and let me just show what happens if I do make blind test here. Yeah, it can compile just like when we had local files, and if I try to compile again, yeah, it's up to date. And if I run blind test, it says version 1. And remember, when I changed from version 1 to version 2, it was the local file on the local computer, not the one on the server. And if I go to this one and change version 1 to, let's say, version 3. And compile it up here. Yeah, I compile it. And if I look at the timestamps, you remember that my local computer, the one called Jobotron, its clock was a bit wrong. So you see that the file I just compiled, called blytest, which is located on the remote server, it got a timestamp of 1333, while the local clock says 1336. So this is a bit old, this file. Now, make looks at the timestamps, so to show problems here, I will look at the make file. So in the make file, you can have more advanced rules than just compile the C program to make an executable. What this one says is to create a file called blytest in the parent directory to this directory called remote. I will compile the same blytest.c, but put the resulting executable file in the parent directory. So I say make, and then it will just use this rule in the make file, and it compiled it. And if I try compile it again, well, it says it's up to date. If I edit, blytest.c, the one that says version 3, and change it to version 4, and then try to make again. Oh, now it's wrong. It says blytest in the parent directory is up to date, even though I just edited the file here. So if I run that program. It says hello world version 3. And if I look at the source code that I just built, just edited, it says version 4. So it did not realize that I had edited the file because the timestamps are wrong. Maybe it's late enough now that I can try make again. No, still up to date. Because again, if I look at blytest.c and if I look at the executable, it still thinks that blytest is newer than the old, than the source code. And it doesn't really matter if I wait, because these timestamps on the files, they won't change just because I wait. But if I edit blytest again and try to change to version 5, and now I list the times. Okay, now it says 1337. I don't know, I can see the seconds here. So maybe if I try make again, no, still not. Still the source code is older, it thinks. So maybe if I edit again and version 6. No, wrong. Maybe now I can make? Yeah, I could. So after editing the source code several times, finally make realize that it's newer. Just because the files on the remote server uses the remote server's clock, and the local files, like the executable blytest, uses the local clock on this computer. So this can be quite annoying if you're working with remote files and you have unsynchronized clocks. So, what do we do about this? Well, the first thing we need to do is to try to synchronize the various clocks. Just as I talked about this infrastructure of clock synchronization. Phones, watches, and all sorts of computers. And that may or may not be very easy. Let me move to the same slides I've been using before, the ones I stole from Erik. This one. And this is about chapter 5.1 and 5.2, which talks about time. And one reason, or one thing to think, important thing in distributed systems is sequences. Things happen, but in which order? So did I edit the source file first and then compile it, or did I compile the program and then edit the source file? That's a typical sequence. But it's important for other things like coordination. When we have several nodes in a system try and cooperate in some way. When we have a service that is used by different nodes, and we have, let's say, a first come, first served algorithm to choose who will be working next. Yeah, which one came first? The edit or the compile? Deadlock-free transactions. When we work with transactions, timestamps can be very important. And as we saw here, software management, make, for example. And also, if we have real-time systems where the actual time is important, not just the sequences. Maybe I need a guarantee that I get a reply from the control system for the airplane within 1 second, so we can move the rudders so the plane doesn't crash. Or timestamps in cryptographic protocols, similar to when you have a certificate in your browser and the one on the server is outdated. When you communicate encrypted through a radio link, you may need to have the clock synchronized, so the encryption and the decryption are in sync. And of course, authentication and authorization tickets. If I log in on a single login system, then I need to know when was that ticket issued and how long, well, when will it expire? And then the actual time is important, not just the sequence of things. And just to illustrate problems with local time and sequences, we have Martin and Anna who are sitting on mountaintops, and then we have Eric, who is also sitting on a mountaintop. And you know, the speed of sound is like 300 meters per second. So if Martin is 1 kilometer away and Anna is 2 kilometers away from Eric, then it will take 3 seconds for Martin's honk to arrive at Eric and 6 seconds from Anna's honk. And if, let's say, Anna honks her horn 3 seconds before Martin does, in reality, I mean, this is the real actual times they use. Well, Eric will receive that honk before, will receive both honks at the same time. But Anna hears her own sound before Martin's has arrived, and the opposite for Martin. So we have 3 different observers and 3 different sequences of events, just because of the delay, the latency in the sound. And maybe if we have longer distances, now it looks like they're all on the same planet at least. So when Eric lights his lamp, and Anna and Martin start to, or go to the meeting here. If it is much further to Anna than it is to Martin, then even the speed of light will be different. So let's say Anna is on the moon, then as you may remember from a previous lecture, it is 1.3 light seconds to the moon. So Anna will arrive a little bit later. And we haven't even, we're not going to talk about relativistic effects. Maybe you have studied some physics and know that, okay, someone is lighting a flashlight on the moon, someone is lighting the flashlight on Earth. If I am on the Earth and I see the light from the flashlight on the moon, and then turn on my flashlight, then yeah, the moon flashlight was turned on before I turned on mine, because the light had time to arrive. But if I and the person on the moon try to light our lamps at the same time, then it depends on the observer. Not just when the observer sees the lights, but the order of the events are actually not defined in a global way. So it depends on the observer. If someone is moving very quickly past the Earth and Moon, it can look to that observer as if I turned on my light first, but it can look like to a stationary observer as if the other light was turned on first. And again, not just because of various ways of seeing it, but because simultaneous events are not globally defined. So either they were the one happened first or the other one happened first. It depends on the observer. Okay. What we will be talking about in this lecture, and I think the next one, is temporal sequences, physical clocks, actual clocks that show times like 1346, and algorithms to synchronize those. If you have heard of NTP, Network Time Protocol, it is a way to synchronize clocks on local computers. And we will also see logical clocks. Sometimes we're not interested in or may not be able to determine actual times. So we have logical clocks instead and try to synchronize them. But more about that later. And here we have the make example that I just showed. So let's skip that one. And go on to UTC. And as you remember, one of my computers here had a completely different time zone. Not really true. It's more that the shell, the command interpreter I logged into, was not set up to show local time the same way as this one was. But what is UTC? It is coordinated universal time. And if you look at the abbreviation, coordinated universal time, how does that become UTC and not CUT? UTC. Well, in English, it would have been coordinated universal time. But this was something that the British and the French were trying to agree on. So the French call it temps universel coordonné, which would be TUC. And of course the British would not agree to that, and the French would not agree to this. So what they did was move around the letters and compromise in a way that it doesn't actually mean anything, but both can be equally unhappy. At least they're not calling it Greenwich Mean Time, so that would be much too English. So this is a universal time standard. And if you have a server or any system that works with different time zones, or just that suddenly someone decides to have daylight savings time and move around the clocks just because it's summer, UTC is probably what you want to use in your system. And it says here you have various institutes working with this. They have atomic clocks that are very precise, and they have a weighted average time. And GPS satellites, well, GPS is a good way to get a very correct time. You know how GPS works. You have satellites, and to find out exactly where you are, you have to measure the time it takes for the radio signal from the satellite to reach you. And you have several satellites that you talk to, or rather listen to. You don't send anything to the satellites. And each satellite has a very precise clock, and you get access to that through the GPS signal from the satellite. So you can get a very, very precise time. And I read yesterday that you could get around tens of nanoseconds. You need special hardware. You need an antenna on the roof so you can can receive from several satellites at the same time. So this is extremely good. I mean, how long is 1 nanosecond? Well, it's about this long. The speed of light in vacuum is 30 centimeters per nanosecond, but it's a bit slower, the electricity in copper cable, so maybe 20 centimeters. So you, maybe this is 2 meters long, so 10 nanoseconds is about this cable here. So that's extremely good. If you have just normal time synchronization, we're coming to that. Also, before we continue, length of day. Yeah, just to show that, is there really a real actual time? Well, it's a bit difficult. It's not that the Earth always has exactly the same rotation speed. So sometimes a day turns out to be a bit longer or a bit shorter than what all your atomic clocks show you. So as you can see, and if I zoom in on one part of this, July the 5th, 2024, it was sort of 1.6 seconds slower, or rather faster, because the Earth is rotating faster, making the day shorter. And maybe you've heard about these leap seconds that you sometimes add to UTC, just because the Earth has slowed down or sped up. So once in a while you add an extra second, or subtract an extra second, or maybe 2 seconds. That is why when you have time functions in your operating system, you can have seconds that vary from 0 to not just 59, but 60 and even 61. And if you have to add 3 seconds, it will be 62, because sometimes the clock is adjusted. So the Earth is not as precise as we want it to be. And something that's even less precise are the computer clocks. You saw that my office computer had drifted like 2 minutes. And that is, if you look at the local clocks in computers, not the gigahertz clock that runs the CPU, so to speak, but the real-time clock that is set to an actual time. You have a resolution of about 1 nanosecond on each tick of the clock, but it drifts around 1 second in 11 days. And 1 second in 11 days, how much is that in a year?
Around 30 seconds.
Yeah, exactly. So you can expect your computer clock to drift half a minute in a year. And if I install the OS on that computer over there 3-4 years ago, then yeah, I could have 2 minutes of drift. And of course, if you have 2 computers, one may drift one way and the other may drift the other way, so you can have a full minute's difference in a year. But to avoid that, you synchronize your clocks to UTC. So let's move on. Drift effects is just what I said. So we require synchronization because 2 minutes of incorrect time is more than I would accept unless I had to show this once in a while and wanted it to be wrong. When we look at how well our local clocks follow UTC, the actual time, one thing you should remember is the precision of the reference clock, which is very good if you use UTC, the actual time that is used for reference. If you have a reference clock on another computer that drifts just as much, then it won't help. Also the jitter, that is variations in latency. You remember your UDP experiments where one packet could take 10 milliseconds and then suddenly one took 100 milliseconds. So if you use that to synchronize clocks, you need to be a bit careful, because otherwise that jitter of the signals may be introduced into your local clock and set it wrong. And as we said, the local clocks drift. That's why you have to synchronize them. And what kind of synchronization algorithm are we using? Some graphs showing the same things I just said. If we just look at this one here, you have a perfect clock, yeah, you have a fast clock and you have a slow clock, so they drift apart, let's say 1 minute a year, in the worst case. And you can calculate various, how often do I need to resynchronize? How often do I need to get the actual correct time? And if you have a certain limit on how wrong you allow your local clock to be, you can calculate how often you will have to resynchronize. So if it's okay with half a minute, then it's enough to do it once a year. And before we take a break, let's look at what NTP, the Network Time Protocol, does in the simplest case. You have a time server that has the correct time, and it gets the correct time from another time server that is maybe gets its time from another time server, which gets its time from the actual UTC atomic clocks. And what happens is that you just ask, this client here asks the time server, what is the time? And the time server replies with 11 minutes 55 seconds, 0.000 milliseconds. Now, this, of course, can go wrong in various ways. First, have we forgotten the latency? If it takes 100 milliseconds on a bad network to get the reply, this number 2 message here, okay, then our local time when we set it here will be 100 milliseconds wrong. And maybe the time server also is wrong. But we can mitigate this by using some formulas to calculate the actual time. But let's do that after the break, okay? 15 minutes break. So let's continue with time synchronization. I forgot, your time servers are classified according to stratum 0, stratum 1, and so on. And the lower the number, the closer they are to the reference clock. So if I connect to a stratum 4 server, it is get its time from a stratum 3 server and so on. And I forgot if stratum 0 was the clock itself or the network connected computer. But stratum 0 is the clock itself, so you cannot connect to a time server with a better stratum than 1. I also found this one, the server called NTP.oru.se, which I think at least is the university's local time server. And if you look at the ping times, Okay, 16.3 milliseconds, 3.5, 4, 407, 304, up here 8.87. So it varies a bit. So if you use the ping times as an indication of how precise your or how timely your replies from the server will be, this is not extremely good. Suddenly it takes 16 milliseconds instead of 3. So we need a way to mitigate this jitter in the latency. So back to the slides. And it's called Christian's algorithm. That just means ask the time server what time it is, and the time server replies with the time. To mitigate the time it takes to get the message first to the server and then back, we can calculate the round trip time. So if I send the request to the server at, let's say, time 10 milliseconds and I get a reply at time 20 milliseconds, then sending to the server, listening or waiting for the reply, getting the reply, and also any processing done on the server took 10 milliseconds. So to correct for this time here, the time it takes from that the time server says that, okay, time is now 14:26, 22.941. And until that time, that message with current time from the time server arrived at my local machine, I can just take the difference in my local time, not the time I got from the time server, because that's from the local clock of the time server, so that we will use later, but just the difference in my local clock from when I sent the request to when I received it. And if you assume that it takes probably the same time to go from the client to the server as from the server to the client, then you can just divide this time difference by 2, so you get an estimate of how long it took for the reply from the server to arrive at the client. But you remember the ping times, 16, 8, sometimes 3. So we may need to do a lot of these measurements and calculate an average. It's not just, well, I mean, suddenly it could take 100 milliseconds. That does not mean that it will always take 50 milliseconds. Just, and we need this time, this transmission delay, so we can add that to the time from the server, because the time I get from the server was the server's local clock when it sent the reply. If we look at the next problem, it is that how long does it take for the server to process my request and send back the reply? Hard to know, but if we let the server get the local time from the local clock immediately before sending back the reply, not first get it and then put it in a queue and sometime later it sends it away, then the time from the local reading the local clock until it's sent should be short. Meaning that this term here, the time for the server to process, could be ignored. Limitations of this. Christian's algorithm, just as I said, it means what time is it? Oh, the time is. Scalability, the time server is a bottleneck. We have these different levels, different strata of time servers. So we don't have to connect to the same time server it's not that every computer in the world connects to one single time server, but we have this pyramid structure of various time servers that talk to higher level time servers. The jitter, especially in wide area networks, I mean, if you have a local network, yeah, NTP to our local ntp.oru.se varied a bit, but it wasn't suddenly several hundred milliseconds. And failure tolerance, well, the time server, it says here, it is a single point of failure, but that is not much of a problem because you can have several that you can connect to. The university could have NTP1, NTP2, and so on. Time monotony, what does that mean? Well, don't jump backwards in time. So let's say my local clock is 11:59:59. It goes on to 12:00. It goes on to 12:01, so 1 second past noon. And I get a new time from the time server, and it's 11:59:59. So my clock was 2 seconds too fast. And when I get this new time, I reset my local time from 12:01 to 11:59:59. But this job I have set up to run at noon every day. Well, now it will be noon twice, and it will be run twice. So we try to avoid jumping backwards in time. We don't set our clock to a previous time. So instead, we slow it down a bit. So you may have seen that when you connect to a network and your clock starts going slower. Why does it do that? Well, it is so it can get to the correct time without having to jump backwards. And the same thing with jumping forward. If it's 11:59:59 and you had this job set up to run at 12, and it jumps to 12:01, then you miss 12 o'clock. So you may want to just speed up the clock instead of jumping forward. And sometimes when it's too much, the difference between your local clock and the reference clock is several minutes, several hours, then it says that no, I can't do this. So you have to manually set the time to the actual time, and then of course it jumps, but then you're aware of what happens. Another algorithm, not Christian's algorithm, that means what time is it, the time is. Here is another algorithm that you can use when you don't have a reference clock. Let's say you're on a submarine, and on the submarine there are several computers that need to be synchronized with each other, and there is no way to communicate with the outside world. I guess many submarines have atomic clocks that are very precise. But what you can do is you use one of the various computers as a server, or just any computer could decide to become a server for the Berkeley algorithm. And the time server asks all the other computers what time it is. And then it just calculates the average. So if they replied 3:10, 3:09, and 3:14, the average of that is 3:11, and the time server itself should also be part of this. And then you don't change the client's clock, but you reply with an offset. So you tell client 1 that, okay, you're 1 second too slow. You tell client 2 that you're 2 seconds too slow. So in the future, they can add this or subtract the 3 there from their time. So they have a better estimate of what the time is. And probably you want to remove outliers first. So if the clock say, if you have a client number 4 that says it's 1970 now, then remove that one, because otherwise you would have chaos in your time estimates. Pros and cons of this way of working. Well, both pro and con that no reference clock is required. Pro, because you don't actually need a reference clock. If you don't have one, it can work, you can use it. But you can't get a better estimate of the time from the outside. No single point of failure, because any client, any computer on the submarine can decide that now I want to start a synchronization. But scalability may be, if you have many computers, the server has to handle all these replies that it gets and then send out the new time, what to add and subtract from the local clocks. And the interval of synchronization, yeah, it depends on the worst clock of all the computers. So maybe you remove outliers first before you do anything else. Let's say something about NTP, the Network Time Protocol. That is what we're using. What I should use on my office computer if I only had set one time server that could be connected. Reliable, scalable, synchronization with UTC. Even under changing message travel times. So it may take first the jitter when connecting to the local time server, the ntp.oru.se. It could vary from 3 milliseconds to 16, just when we tested it. But also, it may be much longer when you when you connect to time servers on at other sites than locally on the university. Precision. How good is this? Well, 10 milliseconds or so in a wide area network. It's not a local network. 1 millisecond in a local network. So even if the NTP server at the university, and I'm not sure if it's actually at the university, it could be somewhere in Sunat, we can get 1 millisecond or so. And if we have a local UTC clock, such as if we use GPS, the GPS signal, then we can get down to 1 microsecond, which is 1 millionth of a second. And as I said, with special hardware, 10 nanoseconds, but then you need to receive the GPS signal yourself. Then it's not really using NTP to get the time, then you're using GPS to get the time. What about reliability and scalability? Well, what happens if someone announces the completely wrong time? Well, I don't think I can answer that. I'm sure if someone pretends to be our local time server, unplugs it, plugs in their own computer, and sends incorrect times to mess with our security system, for example. I think there is, I haven't looked at that, I think there is a more secure NTP either being developed or developed, so you have some sort of certificates or keys that allows you to check that you're actually talking to a real-time server. Scalability, well, this stratum level organization allows you to scale very well. Anyone can set up their own time server for their own local set of computers and only get time once or to one local computer from the next level time server. And here we have the different levels. The GPS radio receiver or the atomic clock is stratum 0, and then it becomes stratum 1, stratum 2, stratum 3, and so on. And since my client is now stratum 4, I can let other computers then becoming stratum 5 connect to this one. So we have a tree where the time flows downwards in this tree. You see there are also connections sideways here. And that is when stratum 2 servers or stratum 3 servers want to synchronize with each other to get a better estimate of the correct time. So far, we had one computer talking to one other computer, but on a local area network, when we can send multicast messages, a single message to everyone on the local area network, we can use that to announce time. So then we don't need a request, we just let the time service send out, periodically can send out a time message. As opposed to Christian's algorithm that we saw, if we cannot use multicast, for example, if we're not on the same local area network, because usually multicast messages are not forwarded through to other local networks. Then we need one request and one reply, as we saw before. And we have this sideways communication between the two different time servers on the same level. And now we have a lot of formulas that shows how we can try to estimate the difference between those local clocks. And let us jump here. Now we have server A and server B. And as I said, they're on the same level, the same stratum. So it's not that one asks the other for the time and then believes it. Instead, it sends a message from server A here. It sends its local time to server B here, which has its own local time. So T1 was when the message was sent, according to server A's time, and T2 is when the same message was received, according to the clock on server B. And then server B replies with the send time when it sends this reply message according to its local clock, and then we receive on the original server A here, we receive at time T4 according to the local clock. And we have an offset, O, between them. So server B could be 50 milliseconds. The time could be 50 milliseconds more than on the other server, for example. So what do? Well, we can calculate a number of things. If I look at T4 here, now let's start with T1 T1 and T2. T1 is the time here. If I add the time for the request to be sent, the latency, and then I would get the resulting arrival time of the message according to server A's clock. But on server B here, I don't have that clock. I have my own clock. So I have to add the offset. How much further is server B's local clock? And then when it comes to reply, we do the same thing. T3 according to server B's local clock, T4 according to server A's local clock, and T4 is T3 plus the time for the reply to travel, and subtract now the offset. And I subtract it, I don't add it, because if I added it up here, then meaning this server B has a higher value of its clock, and server A has a lower value of its clock, so I have to subtract it. Now I have two equations, and what I want is O here. I have T1, T2, T3, and T4 because those are read from the local clock and sent in the message. You see that sync message here contains T1. I have these two equations, and I add them together. On this side I have two of the offsets, T3 minus T4 plus T reply, and then plus T3 plus T1, minus T1 minus T request. So I add them together and get this, and rearrange, divide by 2, so I get that the offset is given by this formula, T3 minus T4 plus T2 minus T1 divided by 2, plus this part. And we don't know T reply and T rec. We don't know how long it took for the request to travel through the network, and we don't know how long it took for the reply to return. But a reasonable guess is that they should be similar. It probably takes the same time to send a message from computer A to computer B as sending from computer B to computer A. That may be completely wrong, but we give, depending on the type of network, we assume it is so. So this one can be removed completely, because one time minus another time when they are the same is 0. And we just take this part and go down here. And our estimate of the offset is T3 minus T4 plus T2 minus T1 divided by 2. So since we sent the message forward and one backwards, we don't need to worry, at least not too much, about the time it takes for the message. And again, you may need to do this a lot of times and then compute an average. And you can calculate an upper bound of the error if you look at the times here. So if it becomes too much, then you may not want to synchronize at this time. Okay, network time protocol properties. Let's look at this one. As we said, if you have a local network, and you can get down to 1 millisecond, but in wide area networks, some tenths of milliseconds. And if you need better, then you can get down to 10 nanoseconds using GPS hardware. Reliability and security, well, if a server stops working, then you can connect to another server, either on the same stratum or another stratum. And as I said before, but I wasn't sure how it has been implemented yet, digitally signed information. So you have some sort of key or certificate. And the scalability, well, you can have this tree of servers that lets you distribute time worldwide in a tree-like structure. Okay. What can we use this for? Well, you remember remote procedure call and various types of failure semantics. For example, at most once, you want to guarantee that when I call a remote procedure, I want it to be executed. Well, maybe it's not executed at all, but it is never executed twice. So one way to do that was to keep track on the server of all the requests we have received, all the remote procedures we've run, and all the replies that we sent. Because if the reply was lost, the client will try again to run the same procedure, but it's already been run. So I can't run it to get a new reply to send to the client. So I need to have a stored result from a previous execution of the procedure to send back to the client, to guarantee that it's run at most once. If each client has an ID, not for each individual call as it says here, but the client itself has an ID, so we know which ID or which client are we talking to, and the timestamp for the original call. So the first time it called this remote procedure. And what does the server need to do? Well, it stores the last timestamp per client, but it doesn't have to store that in persistent memory. It can just be a variable in main memory. It needs to store the results, and as we said, filter duplicates by recognizing that, oh, this has been done before, so I am not going to run this procedure again, but I have the result here, so I'm sending it back. If the server fails, remember we said timestamps stored in non-persistent memory. So if I get a new request from the same client for the same procedure, the server cannot know that this is a new request, so it will happily run the procedure once again, which we did not want because we want at most once failure semantics. But if the server knows at least a rough estimate of its failure, what was the last thing I did and stored, and then it stores persistently, so on disk or on SSD, and flushed to the actual hardware. If the server knows sort of when it crashed, then it can recognize all remote procedure calls that are potential duplicate calls. So if the last procedure I did was 11 o'clock, I know I crashed around 12 o'clock, but then I get a new remote procedure call with a timestamp of 1 o'clock. Yeah, that cannot be something I've already did. But if it's 11:30, okay, maybe I did this. So I should not try to run it again. So I need to store on the server the failure time, or at least the last thing I did before everything crashed. But each remote procedure call needs a timestamp. And of course, the server and the client need to agree on the time. So here we have the point of failure. Here we have those calls we know we haven't run. And these over here could have been run. And if we have failure semantics saying that, oh, at most once, then not running the procedure at all is acceptable. So don't try to run these again. Only run these that we know have not been executed. Run them again. Consequence. Oh yeah, this is the same. So a remote procedure call that was not executed will be considered a duplicate. So these are, well, back to what I said. These, it's okay to not run the procedure at all because it's at most one's behavior. So handling remote procedure calls that were never executed, that's something we leave to the client. And of course, they need to agree on the time. So we need to agree we need to synchronize the time between the client and the server. What is this then? Well, if the client keeps track of the client's birth date, we can call it the epoch. When was the client started? No, I'm getting confused here. Yeah, this is more about handling failures, but I don't remember this part, so I'm just going to skip it. And instead just go to, hello. This one. Other uses of synchronized clocks. As we said, one use was to implement failure semantics in a more efficient way than storing each and every call and each and every reply on the server. Also for synchronizing data streams, we may need the clock to be correct, so we know what time, if it's a video stream, for example, from a security camera. We also have quality of service, and when we have a real-time system, I guarantee a reply within a certain time. Then I need to know what time it is, so I can see if I fulfill this requirement. And when it comes to resource management, what on a local system would be done with semaphores or locks, I it becomes much more complicated when you have several nodes with independent times and no global semaphores, no global locks. So you need to have an algorithm how to use those, how to lock things. And one example is, or one thing you can do here is leases, which are locks with a lifespan. So if I get a lock at, let's say, 12 o'clock, and I never unlock it, well, I only have a lease. So at 1 o'clock, for example, it unlocks automatically. And we talked about authorization tickets, like one single sign-on systems when you log in once and you get a ticket that you can use to use other parts of the system. You need a time for that. It expires after a while, so then you need to know what time it actually is. And you have when you have cryptographic authentication protocols, also for encryption, if you have some encrypted radio traffic requires that the clocks on the two radios that communicate have to be synchronized. So the encryption method uses the time, so you cannot record a message. The enemy cannot record a message that comes through the air, listen in and record it, and then replay it later, which you could if there was no timestamp in the encryption. And we talked about compiler management, like make timestamps on files, and local caching of data, like when you connect to a website and you get back a web page. Okay, how long will you keep that in the cache until you refresh it from the real source, the real server? Next step is logical clocks. And before we finish, I will just say something about logical clocks. As we've seen, if we use local clocks with real time, yeah, we can get down to not without very high expenses, 10 nanoseconds, but with reasonable expense on a local area network, 1 millisecond or so. And on a wide area network, like tens of milliseconds. A lot can happen in 10 milliseconds. So if you have a system where it's important in which order things happen, for example, with locking, who locked this resource first? Who updated this data value last? Then synchronization of actual time may not be enough. So we may need a way to handle sequences of events that are not dependent on synchronizing actual clocks, actual time. So, for example, if you have one node and then an event happens, I write a value to a database, and then another event happens, I write a value. Okay, then clearly the second one happened after the first one because it's on the same node. You can look at the local clock and you know that in the program that did this, one thing was done first and then the other was done. Also, if you send a message from one node to another, then it must be that sending the event that was sending the message happened before receiving the message. But if you have two nodes, each one with their own local clock, and then something happens on one node, and then also something happens on the other node. The local clocks may say that this happened at 11:59:59, and the local clock over here may say that, oh, it happened at 11:59:59.5, so it was later. But if you don't have that precision on the clock synchronization, it could very well be that in reality it was the opposite order, even though the local clocks say give certain times. So we want a way to use some sort of logical timestamp. And we will look at just simple sequences. Okay, this happened here, it was at time 1. This happened here at the same node, it was time 2. The interesting part is when you try to synchronize between different nodes. As we will see, we have something called Lamport clocks that basically says that if I did something at time 9, and then I send a message to you at time 10, I send a message to you, and you receive that message according to your local clock, it is time 4. Yeah, then you need to change your local clock, because if it's time 9 over here, it has to be at least time 10 when you receive the message. And we will also see something called vector clocks, which keeps track of local times at all the different nodes. It gets a bit complicated, but that works to see which events actually do have to have happened in a certain order. But let's do that next time. So finish for today and meet again on Friday, maybe?
I think Friday is only the lab session, I think, for the reason like the lecture.
Let me just check so I don't lie to you. Distributed systems, graphical. Yeah, this is today, and that is just the lab. So we have nothing more this week, but next week on Monday. So no lectures until then. Okay, thank you.